Hello, everyone. I'm Sharini. I'm a master's student at the University of Western Ontario in Canada, and my talk is about the photometric properties of impact melt deposits on the moon. So impact melts are these dark, low albedo features that are mostly smooth in meter scale, and they form as a result of impact cratering, and they are quite commonly found on the moon. These are some images of impact melts. And they have some characteristic morphologies which make them easy to find out. And so when talking about impact melts, they have been studied in both optical and radar data sets. So what we have here is, oops. So what we have, this is not what okay, good. So what we have here is a radar and optical image of impact melt deposits. And this particular Okay, I wanted it to highlight the impact melt, but okay, what we see in the lower end of the crater, which has high CPR, again, the image on the right is a radar mini RF S-band circular polarization ratio map, which can be used as a proxy for surface roughness. And the high surface roughness regions that we see in the southern rim of the crater is basically impact melts. So when looking at the radar data, it seems to have high CPR, which means that it's quite rough, again, in decimeter to centimeter scales. But again, when we look at the optical image, it looks quite smooth. So what we can say is that impact melts look smooth in optical images in meter scale observations, and they look quite rough in decimeter to centimeter scale in radar observations. And this ambiguity in their surface roughness properties can be attributed to the presence of a glassy surface layer on top of impact melts, which has been discussed as a hypothesis by Nish et al. And talking about glass, glass is not something that's uncommon on the moon. This is an example of an impact melt rock from Apollo 16 sample, where we see that the rock is almost entirely covered by black glass. And talking about detecting the presence of glass in impact melt deposits, it's quite difficult to do that in remote sensing observations because glass has quite broad and shallow absorption features. So it does not have diagnostic absorption bands, which make them difficult to detect using its spectral signatures in remote sensing observations. Which brings us to this methodology that I'm using in my study to detect the presence of glass. There is a study that talks about the reflectance properties of terrestrial volcanic samples, where they study the reflectance properties of samples that are glassy and crystalline in nature. And they noticed that the more the crystallinity increases in a sample, the more the reflectance increases. So for this study, I used this property of reflectance of glass and crystalline materials to kind of compare impact melt rocks, which are said to be glassy in nature, and again, comparing them with more crystalline rocks, which are impact melt-free rocks, which are found in the ejecta of craters, which is what I'm doing in this study. And to do that, I looked at 20 craters, quite diverse craters on the moon. Um, Again, looked at the ejecta, the melt-free ejecta, and also the impact melt within these 20 craters. And so I had to first map them. So this is an example of Korlovsky crater that we saw before. And on the left is an example of the mapping. So I had to do that for all 20 craters. And on the right is the bond reflectance map. So this is just an average reflectance product that were created using photometrically normalized, terrain corrected maps that are available for the moon already. So this is the average reflectance in UV and visible bands. So this is the product that I used to study the reflectance of melt and ejecta in my study. So I extracted the average reflectance or the bond reflectance of all these impact melt and impact ejecta in all 20 craters, and which is what we see here that's been plotted against its age. And what we see here is that the impact melts seem to have consistently lower reflectance when compared to the ejecta. And we also see a trend where this seems to decrease with increase in age. And it's also good to note the contrast or the difference between the reflectance of the melt and the ejecta within each crater, which is what we see in this plot over here. We see that the contrast or the difference between reflectance in melt and ejecta is quite high in younger craters, and we see that it's almost close to zero in older craters. And again, we saw a bunch of plots, but talking about what the images itself represent. So again, this is a map of Kolovsky where the impact melt and ejecta has been mapped. And we see a bond reflectance map of the same region. And we see this huge dark patch or dark flow extending out of the crater. On the right, we see that these are impact melt flows. And when we look at the image, the bond reflectance image on the left again, we see that there is a huge contrast between the impact melt flow and the ejecta around the crater, which is what we saw in those plots as well, where younger craters like Kolovsky had a huge contrast. And moving on to a comparatively older crater, which is Laland, we still see that there's this huge dark patch in the northeastern rim of the crater, which again corresponds to impact melt ponds that we see on the right. And moving on to a much older crater, which is Ode, this is the oldest crater that we looked at in our study. And when we compare the reflectance of melt and ejecta, we see that it's almost quite difficult to see the contrast, which is again what we saw in the plot as well, where older craters had less contrast. But what's interesting here is that there's this feature, there's this crater which is sitting on top of Ode crater, and we see this area of low reflectance is flowing out of the crater. And when we look at it in detail, so these are impact melt flows, not of Ode, but the crater within Ode. So what's interesting is to note that there are two impact melt flows in the same region that formed from different craters, and they have different reflectance properties because they formed in different periods. And again, we previously saw how CPR in particular is quite useful in studying or detecting the presence of impact melts. So what we see here is Donnerem crater, and on the left is a CPR of the same crater, and on the right is bond reflectance map. And we see that we can see this huge flow at the northern rim, which we see in both these images, but there is this small limb that's extending on the right of the flow, which we only see in the bond reflectance map, and we don't really see this in the radar and the CPR map. And upon closer examination, so these regions correspond to thin sheets of veneers. I think we see these veneers, and these veneers pop out only in these bond reflectance map, likely because they're too thin and lack the centimeter to decimeter scale roughness to pop out in the CPR map. And so again, this is Copernicus crater, and on the right is a spectral map that was created by Nish et al. In 2022 of the same region. And then on the left, we have a bond reflectance map, again, of Copernicus crater. And when we compare these two regions, we see that there are some spots of low reflectance in the bond reflectance map, which seem to match with the blue areas in the spectral map, which correspond to glass. And when we look at one of these patches in greater detail, we see that this low reflectance and these blue areas correspond to regions of uneven terrain that have melt veneers in them. What's more interesting here is that there is a very obvious impact melt pond sitting right there, but it doesn't pop out as much in the bond reflectance map or even in the spectral map, which is likely because impact melt ponds being thicker might take a longer time to cool, and impact melt veneers might take faster time to cool as they're thin. And so that might form glass when compared to the other scenario, which is what you might be seeing here in this bond reflectance map. And so since we're also interested in studying the surface roughness properties of impact melts, again, CPR is used as a proxy for surface roughness, and we have the CPR values for melt and ejecta in all 20 craters. And what we see here is that the CPR of impact melts is quite consistent in the younger craters until 3. It's quite high as well. It's around 0.9 around younger craters, and then around 300 million years, it seems to go quite low, start going low. And so this might be because of impact hardening and space weathering processes, which might break down these rocks over time. So to conclude, there are three major points that I'd like to discuss. So we did photometric analysis of 20 lunar craters where we compared the reflectance of impact melt and ejecta, and we noticed that the impact melt had consistently lower reflectance values when compared to the ejecta, which might suggest the presence of a glassy layer. And we also noticed that these values diminishes with age. And we also saw that it takes around roughly 300 million years for the impact melts to break down over time. Thank you.